Hello and welcome to our channel again. Suraj here, and today we are going to continue our series on the capacitance and the electrics. And our today's topic is the parallel plate capacitor. So in a previous video, I've discussed about some of the basics of the parallel plate capacitor. So I'm going to quick recap of my previous video on the parallel plate capacitor and to derive out the capacitance and the potential energy stored between the two plates capacitor. So let's start our today's video and let's start begin. So what is generally a parallel plate capacitor? So I have a diagram of a parallel plate capacitor. So it is like a two isolated conductors who have respective positive and the negative charges such that the magnitude of charges are equal on the both plates and they are separated by a very small distance d. Remember, the distance d should be very small due in respect to the size of these two parallel plates, and this is our criteria, and this is the basics of parallel plate capacitor and how it exactly we made the parallel plate capacitor. So we can take two conductors which are electrically neutrally discharged. It means they have equal number, it means they are electrically neutrally. Okay, so let's me draw and to show that how exactly I can make a parallel plate capacitor like a setup. So it is like you can take two conductors which are electrically neutral. And what happened is that it means they are both positive and negative equal charges such that they are electrically neutral. You can make a circuit diagram and you connect a battery or a certain type of the external power supply which can remove the electrons from one plate to another plate. Such that suppose that remove the electrons from A plate to the B plate such that here it's become positive charge and here it's become negatively charged. And you just pick out the electrons from this particular A conductor, so you have to do some external work. That's why I have here a external power supply, and due to this there is a storage of the electric potential energy between them, and that we are going to also find in this video. So now let's start with today's video, and first of all to calculate the capacitance of the two parallel plate capacitor. So what is the capacitance? So first of all, calculating the electric field. So we can calculate the electric field due to this parallel plate capacitor in a very easy manner using the Gauss law. Electric field into the dA, we can take it, is equals to the Q divided by the E naught. So we are calculating the electric field due to this both A and B plates. So you can take electric field E constant as seconds outside of the integration sign and dA, and it is equals to the Q divided by E naught. Simple? Yes. Now what should we do? Next, what we can take is that we convert this dA. So we are extracting a Gaussian surface here, and that's why we are using the Gauss law. So if I construct a Gaussian surface here, yes, just outside I construct a Gaussian surface, and to electric flux through this Gaussian surface, select E and dA. So the integration of dA can be written as the total area A of a capacitor EA is equals to the Q divided by E naught. Next, what we can do is that we can write down as the electric field simply as Q divided by E naught A. And the next thing we can do is that if you want to convert this electric field into some another expression, you can generally do that. How? So you know that Q is equals to, you know that Q per unit area is equals to the sigma. So Q is equals to the sigma into A. So if we put down the value of Q as the sigma into A, the expression of electric field can be written as electric field is equals to the sigma divided by E naught. Okay, so this is our expression for the electric field, and both of the expression are important, but the most important is the first one that we derived it. Okay, so here I will just, yes, these two equations are very important for the electric field, but they both are in the different form. Now, what we can do is that if you substitute this, if you see this equation carefully, it's look like very similar to find the electric field due to the infinite sheet of charge. It means you have studied in your electrostatic chapter, and I'm also going to upload the video on this, that suppose that your infinite sheet of charge and you have to calculate the electric field due to this infinite sheet of charge. The electric field is just equals to this sigma divided by E naught. No, the electric field due to an infinite sheet of charge, positive infinite sheet of positive charge, let's say positive, electric field is equals to the sigma divided by 2 E naught. Then why here is E naught? So remember, here are two plates, not one plate. Positive plate is also, so due to positive plate, if I want to know the electric field at this particular point, so electric field points in this particular direction, and it should be equals to electric field 1. Electric field 1 is equals to the sigma divided by 2 E naught, and electric field 2 is due to this negative plate at this particular point also point in this direction. So both of the electric field due to this infinite sheet of charges, I am assuming that this is infinite because the separation distance d is very small, as I have mentioned in my previous lectures also, that these should be very small. So both of the electric field 1 and electric field 2 point in the same direction, such that I can add these two electric fields to E naught, and if you add this E1 plus E2, it will become E net. And if you know how to add this, then this particular is equals to E naught. Okay, sigma divided by E naught, and that's the same expression that here it is. And as I also said that the E that I have taken here is the net electric field due to this both positive charges, positive plates. Okay, now we have derived the expression for the electric field due to these two parallel plates. But remember, the most important between these two is this. This is the most important equation in the parallel plate capacitor to derive this. So you have to take the value of the electric field as Q divided by E naught A, this thing. Now, what should we do? Now we have to derive the potential between the capacitor. So you know that potential VB minus VA, sorry, VB minus VA is equals to the negative of the line integral of the electric field. And this is the very famous principle also, and the very famous connection between the potential difference and the electric field. Now, there are the two positive plates that I have shown here. So the path of the integration should be from positive plate to the negative plate. So this should be the path of integration, such that your initial potential is VA here and your final potential is VB here. And we assume that we have to take our integration sign, and always you have to take your integration path from the positive plate to the negative plate. Now, there is a d distance between the plates, remember. Now, VB minus VA should be negative, obvious, because VB is of the negative plate and VA is of the positive plate. And VB is less than VA. VB is less than VA. VB has a low potential than VA. It means it should be negative V. So here I'm going to write down here what I said, that VB minus VA should be negative of some V. It should be negative. Okay. Minus V is equals to the negative of the, if I pick out electric field outside and the line integral, and the line is the DL. Now this negative and negative will cut out. Now potential is equals to putting the value of electric field as Q divided by E naught A. And you know that the integration of DL is L, and in this case L is exactly equals to the D, because the path of integration is this. So if this is DL, then DL makes D. So the integration of DL is D. And this is our another important equation, the expression for the potential difference between the two parallel plate capacitor. So this is a very important equation, and with the help of this equation we are going to derive our expressions for the potential energy and also the capacitance. Now, how can I derive the capacitance from this? So if you all remember that, what should be the formula of the capacitance? Now, topic capacitance of the parallel plate capacitor, capacitance. So we all know that capacitance is equals to Q by V. Yes, quite simple. Now, if I put down the value of, okay, C is Q by V, so I put down the value of V here, as Q, Q QD divided by E naught A, QD divided by E naught and here A. Then our capacitance can be written as C, capacitance. So here the C can be written as, if I cut down here Q and Q, so C can be even cut down Q and Q as E naught A by D. The capacitance for our parallel plate capacitor is now derived, and you can see that here the capacitance is not dependent of any of the charge and the potential difference between them. It is just dependent upon your area of the plates and the distance between the plates, d distance and area, and E, where E is called the permittivity constant, and we study also in electrostatics. And in our next few lectures also we are going to see that here E naught can be replaced with the different types of the dielectrics also. We assume dielectrics, okay? So now for now we assume that there is a vacuum. For now we assume there is a vacuum, so our simple equation for the capacitance is equals to the E naught A by D. The meaning I say behind the permittivity is that between these two parallel capacitors, there is no any type of the resistivity it has. There is no type of the medium between these two particular A and B. I assume that it is a vacuum. So for this, our capacitance equation is E naught A by D. Quite simple. Yes. Now we derive our expression for the capacitance. Now we are going to derive our potential energy, which is one of the most important thing, is the potential energy for our parallel plate capacitor, that how much energy is stored in it. Potential energy. Okay, so suppose, okay, potential energy. So let's suppose that there are two parallel plate capacitors here, two parallel plate is there. My diagram is not that much good, okay, but no problem. There is a two parallel capacitor. Now they are electrically neutral. What happened is that I transfer the Q dash charge. I transfer the Q dash charge from plate A, let's say, to plate B, such that now the potential difference. Now if I transfer, suppose that the Q dash charge, before there is electrically neutral, now this electrically neutral, but what happened is that now I transfer the Q dash amount of charge from A to B, such that our potential can be written as Q dash by C. How? So as you can see here that in the potential equation, V is QD by E naught A. If you remember that C is E naught by A, E naught A by D. So can I write this particular potential? Can I write this particular potential? It is equivalent to Q by C. Yes, I can write this. It is equals to the Q by C, because C is E naught by D and D will just on this numerator side and E naught in the denominator. Okay, so I have just written it here that it's V dash potential is Q dash by C. Now there exists some amount of potential energy, a very small amount of potential energy. Let's say it's this du. So we know that we can write du as V into the d V dash into the dq dash, because if you remember the equation, which is V is equals to work done per unit charge, potential is equals to work done per unit charge, and you know that the work done that you are doing is just converted into the potential energy. It means voltage V is equals to this potential energy U per unit charge. And just like I've used this equation, now what you have to do is you have to just using the integration sign. Integration is a very beautiful tool. I'm thinking to make also videos on integration also. Okay, now you have to do is just put the integration on both sides. Oh, okay, now we have to do just putting the integration on both sides and our equation will be there. So now what I can do, I can write it as u, because integration of du is u from initial to final. So initially there is 0 and finally it will be f. Here it is written 0. Okay, so initially it is 0. So u final U final F can be written as here U final is equals to B. If I put down the value of V dash as Q dash by C, Q dash by C, and here D Q dash, and here the sign of integration. And if you remember, the capacitance is a constant for a given parallel plate capacitor until the distance and the area of the capacitors are same. So I can put down the capacitance outside this integration sign, then I'll do the integration of dq dash. Now if you remember the basic integration, then this integration can be evaluated as from where, yes, before there is a zero, there is electrically neutral between the both plates, but now there will be the equal number of the positive or the negative charges on both plates. So it can be evaluated as 0 to Q. Now if I put down here the value of Q, our equation will be into Q square by 2. I'm not putting constant because there is a limit. Now I can write our final expression for our potential energy of a parallel plate capacitor U as Q square by 2C. And this is the very important equation, and our whole lecture is based upon this. So this is our potential energy for the parallel plate capacitor. So this is today's video where we discuss about the different types of things like what is capacitance, what is parallel plate capacitor, capacitance for calculating electric field, capacitance of parallel plate capacitor, the voltage, the volt potential difference between the two parallel plates, and finally the energy stored between the two parallel plates or a parallel plate capacitor. So this is our today's video. Hope that you like our video, and in next video I'm going to discuss about the capacitor in series and parallel, just like we did in the electricity chapter, and then capacitors in dielectrics, spherical capacitors, and etc. etc. So thank you for watching my video.